can we still hear me?
Yes, sir.
Okay, so we're to talk about linear momentum and conditions today. That is what we want to do now. So we're going to look at conservation of linear momentum. We're going to look at momentum. So we're going to look at conservation of energy and as well conservation of linear momentum. What linear momentum is all about. We're going to look at the relationship between momentum and impulse as well. So the other ones there, I'm not sure, but let's proceed in the lecture. I'm not sure if we would be able to go through it. Yeah, we're going to look at one D, that's one dimensional collision, and then for two dimension we might actually skip. And then we talk about center of mass briefly. So here in the picture you see some kind of an accident there. So every accident, don't let me say every accident. Let me just say the picture here is as a result of collision actually. So the accident in the picture there is as a result of collision. You see one car here, you see another car here, so they collided together. So that's what resulted in that destruction that you see. So to remind us of conservation of energy, you do remember that the conservation of energy states that energy can neither be created nor destroyed, but always can be transformed from one form to another. So this is because energy energy is always conserved. So in a or let me say on the system, you always have the summation of the kinetic energy and the potential energy. Kinetic energy, which is energy due to motion, and the potential energy, which is energy stored. You have the algebraic sum. Algebraic sum of everything there equals zero. When we say algebraic sum, it means that the total energy before the collision or before or energy before must be equals to energy after. So initial must be equals to final. So basically that's just what conservation of energy is talking about. So now we need to talk about the linear momentum. So it is a fundamental quantity like force energy. No, should I say uh let me say a derived quantity rather. Don't let us say it as a fundamental. So it is actually derived and the formula we have momentum usually represented with letter P. Momentum is usually equal to product of mass and velocity. As you can see here, the linear momentum of an object of mass n moving with a velocity v is defined to be the product of the mass and the velocity as shown here. And as well, it is a vector quantity. That is why you see this arrowhead there. Velocity here is a vector quantity, so this one as well is a vector quantity. So usually, the terms momentum and linear momentum will be used interchangeably in the test as we progress. And usually, momentum depends on those two, like it depends on these two variables. It depends on the mass and as well on the velocity. Are we still together?
Yes, sir.
Okay.
Yes,
So
sir.
so there is a kind of relationship that exists between momentum and energy. So uh the what's it called now? When you look at okay, normally the what we're able to relate linear momentum to is usually kinetic energy, which is Ke equals half mv square. Now, if kinetic energy is equals to half mv square, then how can it be related to momentum? Give me some minutes. Let me get my writing book. Okay, so that we can write on the board. Okay, that's that. So let me refresh this page. You can still hear me, right?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, let's use this page. So we're just trying to relate energy. I mentioned that the form of energy that we easily relate momentum to or momentum with is the kinetic energy. And the formula for kinetic energy is half mv squared. So if your linear momentum is equal to mass times velocity, how can you bring linear momentum into this equation here? So basically we say that this equals half multiply with, you can square these guys together and it will still be equivalent when you divide by m. Do you copy that? Do you get that? You definitely know that it is same, right?
Yes,
This
sir.
this
Yes, sir.
equation is still same as what you have on the other side. Yes. So by the time you put you solve it, you substitute the value of p into that equation. This value for p, which is np, you put it into that, you're going to have half p squared over n, and that is basically p squared over 2n. So energy, actually kinetic energy is related to momentum by saying that kinetic energy is equals to momentum square over twice of the mass of the object. So that's about that one. So let's get back to the presentation. Uh so yes, so two objects with masses m1 and m2, if let's suppose they have equal kinetic energy, how do the magnitudes of their momenta compare? So they've already mentioned that they have equal kinetic energy. So suppose from here now, you could easily transform this is the equation we have, that kinetic energy is equals to p squared over 2m. If we cross this to the other side, we are going to have kinetic energy multiplied with 2m is equals to what? Momentum squared, right? So if a number, for example, let's say that you want to take kinetic energy constant. If your kinetic energy is to be taken as constant, you can basically take the number as well as a constant value. So I want to take those guys as a constant value. Are we together?
Yes, sir.
Yes, sir.
Okay, if I'm to take this one as constant, let's say let k equals 2ke, where this k is equals to a constant value. Remember your variation. You can basically say that then it means that p square varies directly as what? As n. Taking note that the slide already mentioned that what? They have equal kinetic energy. That is why I did that. Suppose they didn't mention that they have equal kinetic energy. You're going to take the kinetic energies as separate entities. That means you're going to have kinetic energy 1, kinetic energy 2. You're going to have mass 1, you're going to have mass 2. Do you get that now?
Yes, sir.
Okay. So this implies that you can basically say that P1 square over M1 equals to P2 square over N2. So which implies that if you want to compare the momenta, you know, let's say you have P1 square, you bring this P2 under this equals M1 over M2. Are we still together?
Yes, sir.
Okay. Which implies that you can basically put the P1 and P2, the two momenta, under a single square to be equal to mass 1 divided by mass 2. Now I want to get just P1 and P2. What do? I basically take the square root of both sides. When I take the square root of both sides, we're going to have P1 to P2 is equals to square root of M1 to square root of M2. So basically, since they did not give us the value for M1 and M2, then your answer is inconclusive because you didn't have enough data. Actually, you're giving masses for M1 and M2 now. Then you can basically try to get the ratio and you'll be able to get which one is bigger than which one is bigger than which one, or which one is smaller than which one. Do you all understand what I'm trying to say?
Yes.
Yes, sir.
Yes,
Oh,
sir.
very, very good then. All right. So here I will say D, not enough information is given because you don't have the mass one, you don't have the mass two, so you can't basically compare the two momenta, right? Now, linear momentum quantity, so it is a vector quantity as earlier mentioned, p is equals to mass times velocity, and its direction is the same as direction of the velocity. So if your direction of velocity is going this way, your momentum go that way. If it is negative x direction, it also points that way as well. So when you are talking about dimensions of momentum, it is ml per t, ml raised to power 1, c raised to power negative 1. I hope you still remember your momentum, your dimensions and units very well. I hope you still remember.
Yes,
If
sir.
momentum is equals to mass times velocity, and mass is measured in kilogram, and you have your velocity in meters per second, so that means units for that guy will be kilogram meters per second, and then in dimension, that is capital M L C is to power negative 1, right? So that is that for that. So you can have this momentum in different axes. So in different axes, you can have the one along X, the one along Y, the one along Z. So what varies in each of them is just the coordinates. Here the one along X, your V changes to V of X. If the one along Y, V of Y, and vice versa. So importantly, you must be able to know uh, the relationship between the Newton's law of motion and the momentum. So actually, the Newton's law that is concerned here is the second law, right? And the second law is the one that relates the momentum of an object to the resultant force. So remember the second law states that the force that tends to cause motion is directly proportional to the rate of change of linear momentum. Do you copy that?
Yes, sir.
Yes, sir.
Yes, sir.
The Newton's second law. So the force causing the motion is directly proportional to the rate of change. When we say change, that's delta. That delta represents change. So rate, when you say rate in physics, it means something divided by time. There's time involved. So that is that. So which implies that what's it called now? Before moving forward, please note that if momentum is equal to mass times velocity, change in momentum is equal to mass times change in velocity. So it's the velocity that changes as the momentum changes. The mass remains constant. Okay. So if we introduce a constant here, we have that equal, you remove the proportionality sign, multiply with delta P over T. So usually it has been obtained that this K is equal to 1.0 or 1, and then you're going to have F is equal to bring in that change in V, delta V over T, which is equal to M into bracket V final minus the V initial divided by the time, right? So, and this guy gives you mass multiplied with acceleration. So, acceleration in direction of the force. Do we still get what I'm trying to say?
Yes, sir.
Yes.
So let's continue our
Yes,
presentation
sir.
quickly. We still have a very long way to do. So that is that about that. Now, impulse. Impulse is equivalent to um, momentum. Not just momentum, actually. Impulse is equal to change in momentum. So what is formula for impulse? Impulse is just basically uh, force multiplied with the time difference. Okay, let's say time t final minus time t initial. But usually the time t initial used to be zero. So at the end of the day, you are going to have just one time involved, f times t. But if in case you are having two times, you must get the difference between those two times, and then you must multiply together with the given force. So here now, I is the impulse, and the equality is true even if the force is not constant. So it's also a vector quantity, and the direction is the same as the direction of the force. Very important to me. So this is the relationship between the impulse and the momentum. So you have the impulse momentum theorem. The theorem states that impulse acting on a system is equal to the change in momentum of the system. Basically, that is very simple. So impulse, that is F must start with change in T, which is this one. So equals to your change in linear momentum as seen here. And what is the change in linear momentum? Mass multiplied with the final velocity minus the mass multiplied with the initial velocity. So say calculating the change in momentum. So you have your change in momentum here. That's formula. That's P after minus P the momentum before. So which is n after minus n velocity before. When you take, you know, when you take the common variable, the common variable there is the mass. So you're able to what, factorize. You bring out the mass and then you have v after minus v before. So that is that. So for this one now, the what's it called? You might be asked to calculate the what's it called? The change in linear momentum of an object after rebound, like after it rebounds from a surface. So suppose it's moved downward with a velocity v and then it bounce back with the same velocity v. Are we together?
Yes, sir.
Okay. Suppose you have an object hit a surface with a velocity v and then we bounce up with the same velocity v. Let's say you want to calculate the change in linear momentum. This is it here for a rebound surface. The other velocity is going to take negatives so that at the end of the day, you're going to have summation there. It's going to add up. So this one is the one moving in what's it called now? Negative x axis. That's the v initial now. That is v initial. This one going up is the one in the positive y axis, and this is the final. That's the after. So after, which is positive, minus v, which is already in negative, and so that's minus v. That's why you see this here. So you have to. Okay. So this is also a kind of a picture where you have a collision. You have this vehicle collided with, let's say, a wall or a surface that is static, something like as you've seen here, body with a car with a velocity 15 meters per second. So the negative x-axis hits the wall. So and also
Oh,
there is some rebound back with a velocity of plus 260. So let's look at this question. In a crash test, who is that? Whose mic is disturbing me? Whose mic? Khadija. Okay. So let's look at this question. Suppose you have in a crash test a car of mass that's 1,500 kilogram, that's 0.2 1.5 times 10 per 3 kilogram, collides with a wall as we've seen here, and rebounds as shown in the figure. This is the collision and this is rebound. The initial and final velocities of the car are, you have the v initial, which is negative 15 meters per second, and the v final, that is 2.6 meters per second here respectively. If the collision lasts for 0.15 seconds, find the impulse. So the first question asks you for impulse. That's question A. The impulse delivered to the car due to the collision. So as you remember, you need to first recall what is the formula for impulse. Okay. So we need to first recall what is the formula for your impulse. So solve for impulse, that is I, equals to mass times change in velocity. Yes, it's the same. That's impulse is equals to momentum, is equals to change in momentum there, which is equals to force multiply with what? Delta T, right? But even if you look at the question, you are not even giving any form of force there. You are not giving force straight ahead. Neither were you giving time. So what are you going to do? You're going to use the mass that you're given. You're going to use the mass that you're given, which is 1.5, and you're going to use the two velocities as well, which is this and this one. So let's take a closer look at the picture. Suppose this is the wall. So that's the wall there. So the object moves towards a velocity of 15 meters per second. That is the v initial. And then by the time it collided, it rebounds with a velocity of, I think we're giving 2.6 there. I guess that is 2.6 we're given. Okay, that is 2.6. So the mass given there is 1,500 kilogram. Are we still together? Are we still together? Oh,
Yes, sir.
Yes, sir.
okay,
Yes, sir.
okay. Now let's look for the impulse.
Yes,
Yes,
sir.
sir.
So it implies that
Yes,
our
sir.
impulse will be equals to the mass. The mass is 1,500 multiply with change in velocity, or let me expatiate
Yes,
further.
sir.
Let me say that, remember that this will be equals to mass into bracket v final minus v initial. Now this impulse will then be equals to the mass is what? 1,500. Please, you need to take note of the directions. This is moving in negative x axis and this is moving in positive x axis. So the one in positive, you're going to open a bracket, 2.6, that's positive, minus, there's already a minus there. Now the v initial is moving in negative x axis. So v initial, because it's moving in negative x axis, that will be minus 15. So that will be minus 15. Are we together? Are we still together?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay.
Yes,
Yes,
sir.
sir.
Yes, sir.
All right, no problem. Whose mic is disturbing? Okay. Animal Sharon, can you hear me?
Yes, sir.
Okay. So by the time we do the mathematics there, that will be 1.5 multiply with this will be 2.6, changes to plus 15. So that will be 1.5 multiply with this is what here? 17.6, right? So,
17.
someone should multiply that and give us an
Yes,
answer.
sir.
26 what?
26,400.
26,400.
Okay, 26,400 kilograms meters per second. So to convert 26, this is 1, this is 2, this is 3, this is 4. So we're going to say that is 2.64 times 10 to the power of 4 kilograms meters per second. Okay. So the next questions ask that the size and direction of the average force exerted on the car. So you want to look for the size, that is the magnitude. This is talking about the magnitude, right? So you want to solve for the magnitude as well. So let's calculate the force then. So yes, you're given time. The time given there is 0.15 seconds. So we need the time. So if time is equal to 0.15 seconds, right? So already you've gotten your impulse. Impulse is equal to 2.64 times 10 per 4 kilograms meter per second. So you know that your impulse is equal to force multiplied by your delta t. However, this your delta t is already that's we don't since you don't have another time, you're just going to say 0.15 minus 0. So your impulse now you have 2.6 watt and cells per 4 equals to force times 0.15. So from here, you'll be able to have that your force F will be equals to 2.64 times 10 to the power of 4 divided by 0.15. So when you do the division, what do you get, please?
Sir, they did mistake in the calculation of the other one.
Of which one?
It is not 26,000. It's not 26,400. It is 264,000.
264,000. Okay, is that right? I
Yes,
think I
sir.
shall.
No, sir. Sir,
What's
it's
the
26,400.
26,400.
oh? So it's 26,400.
I'm here. 26,400.
Okay, twenty six
Yes,
thousand
sir.
four hundred. Okay, kilogram meters per second. 26,400 kilogram meters per second. Okay, so yes, 26,400, right? So let's do this division here. 26,400 divided by 0.16. What do we have? What will be the value we're going to have here?
176,000.
176,000.
176,000.
176,000. Are you still having up to that?
Yes, sir.
176,000.
Okay, all right. So we have 176,000 for the first. So quickly we move away from there. Do we have anybody that doesn't understand the solution here? Anybody who doesn't understand? So if everybody understand, they will move forward. Okay, still have a lot of things to do here. So that is that about that. So you have the solution there. 2.64 times 10 to the power of 4 and then 176,000 there. All right. So this is also a question as well. Still the impulse momentum theory, the relationship that we just finished using earlier. So you have a child bounces a 100 gram soccer ball on the sidewalk. If the velocity of the super ball changes from 10 meters per second downward to 10 meters per second upward. Okay, they said the velocity of the super ball changes from 10 downward to 10 upward. If the contact time with the sidewalk is 0.1 second, what is the magnitude of the force between the sidewalk and the super ball? Oh yeah, everybody should try it quickly. We have just 1 minute to do that, or one, let's say 1.5 minutes. I hope you can still hear me.
Yes, sir.
Oh yeah, let's do it quickly.
Yes, sir.
Let's try it out. Once you are done solving, let me know what you get. Anybody got an answer yet? Anybody got an answer yet?